In this video, I'm going to set up another linear programming problem. So this is one of those types of problems where it's going to be very helpful to draw a diagram. So we have two facilities where the mountain bike, the Flatlander, are being manufactured. One of them is in Phoenix and one of them is in Denver. So I'm just going to make myself a little box. And this is going to be Phoenix. And this is going to be Denver. And the bikes need to be shipped off or distributed to Crested Butte, and Santa Fe. This may look familiar because we did a problem similar to this, same basic idea, in the unit on linear algebra with the Maui Surf Shop. So the Phoenix facility can make a maximum of 345 bucks. So I just like to put that number up there. And Denver can make 765. Crested Butte orders 587. At least 587. I'm going to maximum of 345, a maximum of 765, and Santa Fe orders at least 426. All right, now to come up with our first four equations, let's just identify the bikes going from Phoenix to Crested Butte, let's call that X. And then going over here from Phoenix to Santa Fe, that number of bikes will be Y. And let's change this to red. Then the number of bikes going from Denver to Crested Butte, let's call that Z. And the number going from Denver to Santa Fe, let's call that W. Then what we know here is we know the total number of bikes in Phoenix, 345, are going to X and Y. X and Y. So we can say X plus Y. Now, they have a maximum of 345 bikes. Can't send more. We could send less. So that's going to be less than or equal to 345. Likewise, from Denver, we have W plus Z is also less than 765. Now, Crested Butte wants at least 587 bikes. So Crested Butte is getting bikes from X and Z. So X plus Z has to be greater than or equal to 587 because they want at least 587. That means 587 or more. And Santa Fe wants at least 426, and those are coming from Y and W. So Y plus W has to be greater than or equal to 426. But we are not done because we have our transportation costs. The company has a transportation budget of $65.78. So I'm going to put that over here, 6578. And the cost from each facility to each shop are as follows. From Phoenix to Crested Butte is X, right? And so that's $16 per bike. So $16 per bike times the number of bikes. Phoenix to Santa Fe is Y, and that's $25. So 25 times Y. Denver to Crested Butte is 27. Denver to Crested Butte is Z. So we have 27Z. And then finally, Denver to Santa Fe is 45. So that's 45W. Now, their budget is $65.78. Once again, you can spend less than the budget. You can spend an amount equal to the budget, but in theory, we really don't want to spend more than what's in the budget. So less than or equal to. And so we have our constraints. Now, usually I say figure out what we're optimizing first. That's going to come down here at the end. If you would like the total number of bikes shipped to be as large as possible, how many bikes should be shipped from each manufacturing facility to each shop? So the total number of bikes would just be X plus Y plus Z plus W. So we want X plus Y plus Z plus W to be as large as possible. So it appears to me that we are maximizing X plus Y plus Z plus W. And so we have our objective function, and we have all of our constraints. The next thing that we do is we have to figure out what type of a problem is this. Well, we already know it's a maximization problem, but is it standard maximization or is it a non-standard maximization problem? And so hopefully that becomes clear when we look at the inequality symbols. We have a less than or equal to, a less than or equal to, greater than, and greater than or equal to, and a less than or equal to. We have mixed constraints. Anytime you have mixed constraints, you have a non-standard problem. So this is a non-standard maximization problem, which means you need to solve it using the appropriate method. That's it. I hope this was helpful.